with the large velocity gradient, they don't get out very well.
So I could ask a different question, I guess, which is are there plans to take other people's radiative transfer models and maybe work them in? I'm thinking, Keplerian disk would be, there are plenty of existing models that do the full radiative transfer for Keplerian disk.
Yes. The answer is yes.
Yeah, if we find a way to implement that in the shape mainframe, because it's shape has grown like a monster.
Yeah, sure.
In different directions, and if we manage to get it decently implemented, then why not?
Well, but it's actually grown very well. On the previous occasion, I've been rather snide about the previous incarnation of this set of software, and want to apologize for my rudeness to Wolfgang and his crowd, because I think you've really done well.
It really what? Okay, well, I would like to answer Joel. The advantage of the LVG is that it's easily adapted to a three-dimension, very general structure. The shape is expected to work for any structure you can imagine, with all the formations and changes, etc. Right? So using LVG, assuming the LVG approximation, in fact, the excitation of the lines does not depend on the rest of the nebula. So for each point, you can apply a simplified calculation of the line excitation, and then after that you calculate the radiative transfer, the exact radiative transfer equation, and you get the profile and the maps. So that is the advantage of LVG, and always, practically always, the nebula is in expansion, which is really the general case. This is very efficient, and I think it's quite accurate. The problem with LVG is that in some pathological case and some other which is not that pathological, that rotation really cannot be applied. So to study the case of rotating disk, you must use a non-local exact treatment of radiative transfer to calculate just the excitation, and in 2 dimensions. I personally have done that, so we have the calculations, and in a paper we recently published, we really developed a treatment of this kind, so it's not impossible at all. It really is feasible. The question is that for that, instead of using calculations of the excitation which are standard for each point independently of the rest of the nebula, you have to solve the radiative transfer equation in all the directions to calculate the amount of radiation arriving to each point. So the calculation is much slower, and instead of a few seconds, you may need several hours typically to calculate that. It's an iterative process which is not straightforward at all. Also, the shape and shape mode are thought to work for general users, not only for experts or for people who know very well the details of the convergence when you are treating a three-dimensional radiative transfer and molecular excitation. This is really tricky, and for instance, if you are not an expert in these things and you try to use a model of this kind, the first problem you will have to check is that you are considering enough directions to be sure that really the convergence is good, is okay for all the cells in your nebula. And also, for instance, you will have to check that you have considered enough velocities to be sure that the local dispersion, the local profile is well fulfilled by your velocity network. So really, it's very complex. Anyway, we are planning to do something like that, a three-dimension treatment of radiative transfer using shape. The question is, well, in fact, it's very hard to do a code of this kind, but I think that the experts are going to do that from the technical, from the principle. The principles themselves are not complex, which is difficult to do the code. But I think is the next step in shape mode. Okay, it's for people who are not in a hurry to do a fitting, right? If you have several months to work on your nebula, it will work very well. Thank you.
Okay, you want to say something?
Yeah, it was just a quick question from basically, well,